one thing that you will notice if you run this code not in the iPad notebook is that we will see this error message here. And what it says is that your CP instruction is not, the binary is not compiled with these flags. And this is, remember in the beginning when we talked about different instructions, this is now exactly what it's complaining about. It says, my CPU supports better vectorized instructions like AVX, but the binary does not use this. So it was not, the whole TensorFlow library was not compiled to use this, so it could be more optimized. But that's what this message says. So this here depends a little bit on, this is basically what we've already had. It is just to see it in real time, but you can also try out a little bit. I mean, it's not just for presentation. It is, I'm giving you a guide to it, but you're very free to play around with it afterwards, read the text and so on. It's more to give you an overview actually over the notebook. So if we go now further, so what we see here is just we have a for loop which takes 15 milliseconds, and we have this array is added with NumPy and 16 microseconds, so a factor of 300 or something of speed up, which means, just as a side note, Pioneers may be slow in comparison to this, but it's still, in a way, it's adding 100,000 events. It's still a for loop milliseconds. I mean, it's still doable, let's say. But NumPy is way faster. It looks also way cleaner. So let's just use that. As I mentioned before, the TensorFlow is basically like NumPy. If you create here this array, uniform, shape 10, low, high, TensorFlow has also random uniform, slightly different names, fine. And we should usually specify the D type because it's float 32 by default. But we see here random 1 is not a TensorFlow array. This looks very similar. It even has, it says what it's in NumPy. And we even can explicitly convert it to NumPy if we want. And now we got exactly a NumPy array. Also, in other ways, it behaves like one would maybe expect. We can add numbers to it, it broadcasts. We can take the square root of it. You see, this is now the TensorFlow array put into the NumPy. We can slice it as we know it. We can expand it. This is all. So if you know NumPy, then it looks all very familiar. If you don't know NumPy at all, or this kind of vectorized libraries, then this maybe looks a little bit unfamiliar, but this is just some kind of syntax that you can use to play around with matrices, basically. Or we can also create a matrix by basically adding an axis here. Now we have a two-dimensional thing, and then we have those like this. So this is all. The main thing is it's like NumPy. There are quite a few equivalent operations, such as in NumPy, like tf.square root. Now the difference is this returns our tensor as well compared to the np.square root. Or we can also have the sum, basically, which is the tf.reduce. So instead of sum, we can say over with axis, we have now a two-dimensional matrix. We can say just sum over this axis, which is, it's exactly the same as in NumPy. So if you're unfamiliar with this, then you can also read through other tutorials that explain this more. This is more about what's the difference to NumPy, so TensorFlow versus NumPy. One difference here is that the D types are taken a little bit more picky by NumPy, meaning that NumPy sometimes just converts automatically integers. TensorFlow is more picky with that and wants this to be explicitly cast. Furthermore, it uses the float 32 as a default, but for this is 5 neural networks. We can have like float 16 and so on. And this can lead to problems because for scientific use cases, we usually use the float 64 to have enough precision. For example, in set-fit, in statistical stuff, in simulations, and so on, sometimes even higher. And this is a typical problem that you will get if you try to do something in set-fit or just interact with TensorFlow, you get a D type. It cannot cast because it says the input is flow 32, but it wants a 64. Just add a tf.cast and your problem is solved. One crucial difference to NumPy is that we can't do assignments, because basically it doesn't make sense from a logical point of view. If we have our graph and we do this declaratively, we just say add A to B, the output of that, multiply this by D or whatever. So we're just telling him what computation we want to do, but we're not telling him that certain values that we override certain values, that we change the value of a tensor, I mean, of an array, because there is no array. We're just giving him instructions on what to do. So we cannot say the value of this array takes now this and this value, because there is no such thing as this array. There is just this output of the operation. I mean, think of if you do it algebraically, you calculate something with vectors, it doesn't make sense to assign something. You can just say, okay, we have a new value which is composed of this part of the vector and this part of the vector, but you cannot assign, if you do pen and paper calculations, you cannot assign a value to a subset of a vector. You can just assign a value to a name, sure, as we do always in Python, but not mutate something in there. This is because of the whole graph logic. And in eager, while this in principle could work, TensorFlow also forbids us to do that, which is kind of good, because then we don't make any mistakes and we can simply decorate things. Side note, there are assignments possible. As I've seen before, the tf.variable, we can assign things there. So that works, but that's a special kind of object, or let's say in general, resource handlers. Another special object in this sense is also the tensor array, which acts like an array list in other languages, or a list in Python, basically. If you want to put things together, one use case is if you want to do accept-reject sampling, then you want to do a while loop and fill up an array, for example. But this is already quite an advanced use case, so just, you know, this object exists, but you can play around with it, but it's quite advanced. So this means that a NumPy array, fifth element, we can assign a number. If you do this in TensorFlow, this will raise a type error, and the error message says that assignment is not supported. Now, before, I mean, the whole high performance thing is about speed comparisons. So about performance in the end. So let's have a look at what we're doing here. Size 1 is this 100,000, this large thing, and we can do a time it, which just gives us the timing of the whole thing. We can do the same 16 microseconds. We can do the same with NumPy. So we just create the NumPy arrays, and then we do them again. This is now the small one. All right, so this was the big array, just to give you some idea of things. But more importantly, these two fields are relevant. So this is roughly the same as NumPy if you would do it, but this is relevant because random 1 and random 2, they are very small arrays. As you can see here, they're just 10 elements. If you're adding this in NumPy, and if you're adding this in TensorFlow, NumPy is way faster. I mean, a factor of 20 faster here for a very, very small array, like 10 elements. That's not even worth putting an array nearly, but okay. Which maybe surprises, saying that TensorFlow is fast and everything, but this is something that we expected. As I mentioned before, TensorFlow has way more overhead. It tries to be way smarter with things. And this is not efficient if you just want to add 10 events. There's nothing to gain there. So TensorFlow gets efficient for, let's say, a large number of events. We can also say that if for very small computations, we actually don't care whether it's nanoseconds or microseconds. It's anyway very fast. And this is another thing to play around. We can choose here different sizes, and then we can just time it if we sample in TensorFlow and add those two, or if we do it in NumPy. What I've chosen here now is 20,000, which means now we get 300 microseconds basically for the NumPy version and for the TensorFlow version. As we've seen before, if we, for example, use just 10, then NumPy is way faster, but we can also go to something else, 100,000, or let's say 1,000,000 events. So this is now for 10, as we see again, 18 microseconds and 5 microseconds. So if it were 10, okay, and NumPy is way faster, we've seen that. But then if we go to like 1,000,000 events, we have basically the same speed in TensorFlow as for 5 events. There we go. I forgot to execute the cell above. Okay, we have 7 milliseconds in TensorFlow, and NumPy is a factor of 2 or something slower. I mean, there's not too much to gain in the end because NumPy is already quite good. Yes, we now have a factor of 3 slower. So we clearly see around 20,000 events, at least on my 6-core machine, they're the same speed. Going higher, TensorFlow is faster. Going lower, NumPy is faster. And this is one of the things surely to remember. TensorFlow scales way better. And usually the large numbers are a problem. Whether we have 10 or 100, whether it takes 5 or 10 or 100 nanoseconds, that's anyway too fast. But this is the important thing to scale. This is the more overhead. It tries to schedule, it tries to fuse operations, and so on. The whole overhead comes from different parts, but one of them is the kernels. As I mentioned maybe before, there are CPU and GPU kernels, meaning if we now run something like math log, then it tries to look up what implementations. A kernel is basically a specific AOT compiled implementation of a certain operation. What of those do I have available? And we can look at the ones that are, for example, registered for the tf.math.log by giving in number 5. Now TensorFlow complains because 5 is an integer, and you can't really take the log of an integer, which makes sense. What it says is it cannot find a value twice for the node. And these are all the support the registered kernels. So it looks up what's the most efficient implementation that I have. And you see here, for example, it has a GPU kernel. So a GPU implementation, if we have the D-type double, or a GPU for D-type half, which is 16, or GPU for float. And it has CPU implementations. We see, for example, here, while we have CPU implementations for complex, we don't have a GPU implementation for complex, for example. We also have here XLA. XLA is the accelerated linear algebra, which is like an intermediate compiler step. This, for example, would have now the complex one. But this now is a very good example for if we wouldn't have the XLA kernels and just have those two, how we can produce a bottleneck. If we have a single complex operation in there, then this would not run on a GPU. So we can run some stuff on a GPU, some other stuff not. All right, we looked at TensorFlow like NumPy, but the interesting thing actually is TF function. We've seen the things before, we've went through the logic before, but now we see it really in action. You can also play around. What we have here is this example which is important actually with the print and the TF print. We know print just runs when it compiles, and TF print runs when it executes the graph that is associated to the add log function. And as mentioned before, so if you run this first, then we get running Python, sure, and like afterwards the graph is built, and it also runs the TensorFlow one. As we don't notice it, then we get something out. As mentioned before, if we're giving in 2 new Python objects, this now creates a new graph. So if you run it like that, it runs again Python. So just to basically reset the compilation, we do another log. Sorry. I overlooked something. Sorry, my bad. Here we do not add the TF function at all. right? This is just, sorry, this is not compiled at all. This doesn't create a graph at all. It's just every time runs this again. So if you run this again, then it runs, of course, Python again. This runs eagerly, like NumPy. There's no difference, right? So we can execute it as often as we like, and we always get running Python fully. Every line is executed. Sorry, that's my bad. What we have here is, if you decorate now this function with this, now we're going to have a different behavior. Meaning, if you run this once, we have Python run because we compiled the graph, and we have running TensorFlow. If you now run exactly the same thing again, we expect not to see Python again, but to remember that for input 1 and 2, it should only run TensorFlow. There we go. If you run it again and again, we just have this. The point I made before with the Python object means that it will remember now for 1 and 2, this can be run, but not for 11 and 21. So if you do execute this line, it compiles again. Now remember for 11 and 21, so if you run this again, it's just not. We can also rerun this line again because it remembered 1 and 2, so it also has this. It has now 2 graphs associated, one for the 1 and 2 and the other one for 11 and 21, which of course is completely unfeasible. We don't want to compile it for every input. The idea is that we compile it once for some input. And what we can do here is use TF constant, because now we don't have a Python object, but we have a TensorFlow algebraic expression, basically. Meaning if we run it, now it compiles because it's the first time that we get a tensor inside there. And now we run it with different numbers, and we don't get the Python compilation anymore. So this is basically the example that we had before with what we do here is we get an input x. We multiply this by a random number generated by NumPy and the random number, and we return something else, which is x multiplied by the random number generated by TensorFlow. As you may remember before, so now we run our Python again, it's compiled, but it doesn't really matter. We get now 2 values back. As remember before, the NumPy thing, that's static. So if you run it again with the same input, we expect the first return value not to change, because this depends only on the input and a random number from NumPy, which is now statically assigned to the graph, while the second one is a TensorFlow operation, so we expect this to change. So running it, we see the first value stays the same, the second one changes. We can also use a different input, a factor of 2. Again, the first one is just multiplied by a factor of 2. The second one is multiplied by a new random number. We can also just repeatedly run it, and we will see this first number stays constant, the second one changes. This is really this kind of things. Python is just traced and constantly added compared to TensorFlow, which stays dynamic. So with that, it means we now have just very small examples, but we can have large functions. We can have thousands or 10,000 lines of code that is mostly Python and that tries to figure out what's a good way to stick together a graph. How should our computation look like? Typically for complicated physics function, I don't know what fields you're in, like amplitude analysis, if you know that in hydrogen physics, or any kind of thing, basically, that can be very complicated and you have to figure out which things to stick together. We can call all them, and it all remembers the TensorFlow operations. Another specific thing is the shapes. You may be used to that from NumPy, and it's very similar in TensorFlow, but there is one crucial difference. TensorFlow tensors have 2 kinds of shapes. They have a static shape, which you can access with x.shape, and they have a dynamic shape. The difference is that if we just create a constant as before, then the static shape is just a scalar and the dynamic shape is the same because it doesn't change. So sometimes they coincide, but sometimes, as we do in this example you see here, we say, so we get in an x, and then we say, which is we put in a random number from before, we say just take the x that are larger than 3.5. We have now, while we define our computation, we have no idea what the shape afterwards is going to look like. Before we know it, because before we know what's the shape of random that we're giving in, and then it compiles for this shape. But afterwards, we don't know. So the static shape in the beginning will be 10, because random has exactly shape 10. And the dynamic shape, which we get by calling tf.shape on x, this doesn't look so obvious, I agree, will also be 10. I'm using here the print because this is Python code that runs, and I'm using here the tf.print because this should evaluate this tensor. So this is now a tensor. This is a dynamic shape. This can change during runtime. We don't know it. We will see this below here, which is if we now print the shape of x statically. So when it runs through the first time, it just prints the shape of x. It adds this to the node. It knows, okay, our new x will be only the x that are larger than 3.5. And if you ask it again here on the compilation, what's your shape now? It doesn't know. So it's none. While afterwards, if it runs a graph and it runs a tf print and the tf.shape here, it prints whatever the shape really is there. So if you run it, this is what we get. That's a little bit of race condition here. But it basically means the static shape first is 10. That's what we find. This is in the compilation step. And then it goes through this line. It doesn't know anymore what's the shape. So next time we ask it is, what's the shape? It says it's not. So now if we want to rely on the shape inside here, we could say x.shape equals whatever not. We can't do that anymore. It's now none. We can though explicitly set the shape if you ever need to do that. And tf print though first prints 10 and afterwards it prints 8 because this is a node in the graph. So this is a dynamic shape. This is specified during the runtime. So what we can do, which is building a matrix here, and we have now this tf.shape, or we can also use the dot shape, but the tf.shape is like this is dynamic, right? The shape is specific. We can access this now. So we have now a two-dimensional matrix. And we can now, for example, say, okay, what's the shape, but what's like axis 1 like? So this is now 10. Okay, they're the same now, but this means, okay, in axis 1, we could also go for axis 0, for example, which in this case is also 10, but it just returns us basically a shape with like 2 elements in there, which is 10 and 10. We can do exactly the same for a static shape. Just remember, static shape inside a tf function, decorated function, can be none. On the other hand, you have the variables. As I mentioned before, this is not a lot of magic. If you have a variable inside, we give in a number. You see again, first it compiles. Now we run again with another constant. We get a factor of 2 in there. Okay. What we do here is now we assign a new value to the variable. Instead of 1, we're going to have 42. Meaning if we call it with the same input argument as here we got 1 back, we now get 42 back. Because the variable, the global variable inside here changed. And this is a TensorFlow object, so it keeps track of that. So this is the example as we've seen above. Actually, this is not so much interesting. This is more relevant. Just to be clear, it's a symbolic tensor. We've seen this already. If we now call numpy square root on that, if we don't decorate it, it says in eager mode, as we've seen, it works perfectly well because we're giving it a tensor. We call a numpy function on an eager tensor. We don't decorate anything, no JIT. It works very well. If we now decorate it, or let's say we compile it by calling this function thing here, and now we call the function that is now compiled, it can't work because now x is not an eager tensor, which is like a numpy array, but now x is the symbolic tensor, and it will simply complain and say, can I convert a symbolic tensor to a numpy array? Because now we're compiling, numpy doesn't know what to do with that option. I mentioned before that there is the TF decorator, which has this autograph thing, which means, again, if we do x greater than y, and we're giving it a tensor, and we don't compile it, we don't have a JIT, it works like numpy. So x larger y, this is like numpy, nothing special. If you want to decorate that with a function and we call it again, it doesn't work. What it says is if you use a TensorFlow tensor as a Python bool, this doesn't work because yeah, it doesn't know the value. I mean, it doesn't know, Python doesn't know where to go. As we've seen before, it's always the same again. I know this is a little bit repetitive, but having this idea in mind is basically the key to understand how TensorFlow works. Basically, what it says here is you could use autograph, and this is what we're going to do now, meaning we allow now autograph to work, which means, all right, now you're allowed to convert some Python code, and we can convert these if and else statements there. Meaning, if we execute it now, the function works. As I mentioned before, this autograph can be tricky. What we can do alternatively, if we want to have complicated code, we can just let it convert explicitly to code and print that. Which means the code above, this one, gets a little bit, yeah, bigger. This is it. This is a little bit hard to understand, maybe. Yeah, I also have troubles, but this is what it actually gets compiled to. So now, if you use autograph, that's the thing I'm saying, pay attention. TensorFlow completely messes with your Python code, so don't try to do too much of magic. So I just added here a little performance section with some, let's say, certain complicated function that we now can compare, just to say that it's the same order of magnitude, basically. What we're using here is not just NumPy, but also number, the compiler for NumPy, if you remember. So first, what we do is we just compile the two things. We compile with TensorFlow and we compile it with number, the huge functions above. And now we have 4 comparisons. First, we have this huge function just using NumPy. Then we have it just using TensorFlow but eager without any kind of decoration. And then as the next thing, we have NumPy decorated with number, so compiled, and we have TensorFlow compiled. And the thing is, number and TensorFlow will be roughly on the same order of magnitude. Both are compiled, both are pretty good things. But the large difference is that TensorFlow is more optimized for its graphs, while number is better in general Python code. And this is also what we kind of see here. So number is it's really a different thing in the sense as TensorFlow, but it can also do something similar. I mean, we see again for something as large as the above, it's factor of 3 for faster, just 3 faster, and even when compiled, even then TensorFlow is still a factor of 2 faster. It's compiled and parallelized. Number can parallelize. Again, this is a large number of events, so it's fine. Another thing we can also do is artificial to have a loop. So this adds more and more things to the graph. So this really blows up the graph, but it's just a funny thing to do and see how that scales if we just do all the computations once or if we gotta do it 10 times. This is just a little bit illustrating the same thing. It's just nice to play around and gives very similar things. So it's not so much of interest now. I mentioned before the control flow that we can add. So what we can do, we can define a true function, we can define a false function, and we can now use the tf.content and say a condition, which again is a tensor because it's a bit dynamic, on true this function, on false this function. It will anyway execute both functions to build the whole graph, but either it goes in this part of the graph or it goes in this part of the graph. We can also do, as mentioned, while loops. We define a condition, which is a TensorFlow condition as well. These are 2 tensors coming in, a Boolean tensor going out. This is the body, which has the same inputs as outputs. We give it in right here. If you look at the examples, they're straightforward. As mentioned before, we can map something, meaning, for example, we can map this sign function on all elements of the array. What I'm going to show here is that the map is, of course, very slow because now we're running it in normal eager mode. So it's like a Python map that's very slow. 12 seconds. I mean, yeah. What we can do, we can create a graph out of it, which means it's already faster. So instead of 12 seconds, we're now down at 1 second. 2 other things. There is a vectorized map, which is very efficient sometimes if you're using it with eager. So we see the slowest is using map like NumPy, second slowest is using map normally with a decorator. Third is then using a vectorized map, which is using more memory but can be optimized. But also to play that, if you're using directly design from TensorFlow, this is undoubtedly, I mean, 12 seconds of a Python mapping basically, because if it runs eager, it's like Python versus these 600 microseconds. So basically, the last thing is, as mentioned, gradients. And this is again just doing some accounting. All I'm showing here is we have this gradient tape, which means now it watches this variable. We can do some operations. And then now it remembers what happened inside here, what happened to var3. So this is var2 to the power of 3. And we can take now the derivative by doing this here. So we say tape that we used here, get the gradient of y with respect to var2. And this is just this, something to play around. There is also Jacobians and stuff like that, but this is the basic principle. So we're basically reaching the very end of all the talk. If you want, you can, these are just some examples that you could try out. And all I'm showing you here is a small bonus, which you don't need to know to use TensorFlow, but I've talked so often about the graph and it's an essential part and all these things. Where is that graph? We've never seen the graph. What is actually this graph that gives us all the magic speed up? And what I'm showing here is it's just some more magic. So we're going a little bit into TensorFlow details. You don't need to know that. We get the concrete function out for a certain thing, and we get the graph out just like that. So all I'm saying is we can get the graph out. Now this graph is nothing else than a collection of all the operations that we've done above. You can go up to a function called tf_func2, and you will see that all these operations are happening inside. What you will also notice there is that I've added the name to two functions there. So if you see here, I added that this log operation should be called Jonas log, and this reduce mean operation should be called Jonas mean. And what we see here, if it now puts on all the operation, we get here a Jonas mean, and we get a Jonas log. And what we can do now, we get now all these operations here, right? The ops. We can, from these ops, we can now, for example, get the 6th last operation, which is this one, the Jonas log 1. And we can say, what's the output of that? So up there, what we do is we take the mean of all the logs. And the output of this operation is a tensor called Jonas log 1, 0. Now, we can also see -4 is the mean. So the mean that is taken from all the log. We can say what are the inputs of this operation. I mean, this is just the ops, it's just this list here. We say what's the inputs and print that. And the inputs are two things. On one hand, the constant, and on the other hand, which is the axis. And on the other hand, the input is the Jonas log because we take the mean of the logs. So we just take it from there. So if you check this now, the output, the zeros are because the list of our log operation is, so it's exactly the same object as the zeroth element of the input to our mean operation. Meaning this whole graph thing is not magic at all. It's literally just a graph that stores all the operations, and each operation will know what's its input and what's its output. They're just simple objects that link to each other. And from that, TensorFlow gets all the magic out. So this was everything for today. Thank you very much for your attention. And are there any questions maybe?